Well, howdy, folks. Well, here we go. We're coming down the home stretch now. Just a couple more chapters and a little bit about organic chemistry, maybe a couple tests for you to look at, and we'll tie a bow around this and call it a semester. So it won't take us too long. Now, this next section, we're going to cover two chapters, electrochemistry and nuclear chemistry. And electrochemistry to me is a nice change of pace because now we're going to talk about something a little more practical, like batteries. And so to discuss batteries, we need to discuss really reaction spontaneity kind of comes up in here, where we want a spontaneous flow of electrons through a circuit. You watched the section on oxidation reduction, and I kind of alluded to the fact that batteries are basically just an oxidation reduction reaction where we've segregated the oxidation half reaction and the reduction half reaction and put them in separate places. Now the electrons still get exchanged, but we force them to go through an external circuit, and consequently we can harness that to do work. All right, well, with this flow of electrons, we need to define a couple of things. Now, first of all, if you had a wire made out of copper, remember that if you shove an electron in one end, it's not that electron that comes out the other end of the tube. It's just everybody moves over a chair. Copper has one valence electron. It's clear out in the fourth shell, easy to delocalize, to push it around. All right, so we shove a few electrons in one end, they come out the other end. All right, so that means on one end of this wire, there must be an oxidation half reaction going on because there's electrons being given up here and supplied to produce this current. All right, but on the other hand, there's got to be a reduction half reaction willing to take those electrons that come through. So again, this is kind of what the chapter's about, is a little bit about reaction spontaneity, how willing something is to give up its electrons and how willing something is to actually take those electrons. Okay, well, let me erase a couple things here and a couple definitions. Okay, so when you're looking at the flow of electrons in a wire, it's much like looking at water flowing through a pipe. If we were to look at, well, how many gallons per minute can go through that pipe? Or if you measured, for instance, water's flowing and you're measuring, well, how many gallons are going through there every unit of time? Well, that would be a measurement of current. And in terms of electricity, that's proportional to the number of electrons that are actually going through the wire. Now we measure current in something called the ampere, A-M-P-E-R-E, the abbreviation being an amp. Well, 1 amp is equivalent to 1 coulomb of charge per second going through the wire. Now that's reaching way back to discuss the unit coulomb. This came up back in Chem 130 when we discussed how Robert Millikan measured the charge on a single electron. And it's measured in coulombs. This is how you measure charge. And the charge on a single electron is like 1.6019 10 to the minus 19th coulombs. I think I told you the story about how he measured that charge with equipment that he kept in his desk drawer. It was just an eyepiece from a microscope, a perfume atomizer, and a little transformer to cause charged particles to move in a mist of oil. And he measured the speed at which these droplets, these oil droplets, moved between two charged plates and determined the charge on a single electron. So anyway, it turns out that if you have a mole of electrons, Avogadro's number, and you multiply that by how many coulombs are on a single electron, it comes up to a kind of an important constant that shows up in this chapter. It's called a Faraday. They use a capital F to stand for the constant. It turns out that 1 mole of electrons going through there is equal to 96,500 coulombs. And again, this is just Avogadro's number times the charge on a single electron. All right, so the number of coulombs that go through here per second would be analogous to how many gallons per minute would go through a hose, for instance. All right, well, one other important definition. Let me erase this. Okay, so current then is how many gallons per minute go through the pipe. But that doesn't tell you with what pressure you're pushing the water through the pipe. And so consequently, if we want to know, well, how hard are you pushing the water? Or how hard are you pushing the electrons through that tube? That's measured in voltage. And the unit volt, 1 volt, is equivalent to 1 joule of energy put on each coulomb of charge. So the voltage essentially is is how hard are you throwing each electron down the tube. Now remember, current is how many electrons go down the tube, but voltage is different. Voltage is how hard are you actually throwing them. And so again, that's measured in joules per coulomb. Now, if we combine the two of those, you figure, well, how much work could we get out of that water that was going through the pipe? If we were, say, running a water wheel or a fan with that water, if we're shooting it through the pipe, well, two things would determine how much work I could get. How many gallons per minute, the current, and how hard are you pushing it, the voltage. All right, let me show you real quick. Okay, well, if we put the two together, the voltage, the pressure with which we're pushing the electrons through the tube, is measured in joules per coulomb of charge. If we multiplied that by the amperage, how many gallons per minute going through the tube, meaning how many coulombs per second? Well, you can see then that coulombs is going to cancel out. We end up with how many joules of energy per second are actually going through the tube. This is a true measure of the power. And a 1 joule per second is defined as 1 watt. So watt's a determination of power, where voltage is just simply the determination of the pressure with which we're pushing the electrons. The amperage is a measure of the current, how many electrons are actually going through the tube. All right, well, let's dig a little deeper then into the theory behind electrochemistry, and you'll see that these units come up. I thought this would, at least help grease the way to see the derivation of these units before we start talking about them. All right, well, let's get into electrochemistry. Okay, well, before we really dig into the background and number crunching of electrochemistry, let's take a little more commonsensical approach to this. It turns out that we've developed kind of an intuition over Chem 130 and 132 about what elements like to become cations, for instance. Well, in that process, they're being oxidized, they're losing electrons. And you know that happens with the metals on the left side of the periodic table. On the other hand, the nonmetals, they seem to like to gain electrons and become anions, and so consequently, they're being reduced. So we've already kind of approached this oxidation reduction idea. We just never looked at how do we harness that in order to get some work out of the deal. Well, if we were to look at, well, what elements of the metals that like to become cations like it the most? Well, what jumps out would be like the group 1 cations, lithium, sodium, potassium, rubidium. Very reactive, very big oxidation potential. They would love to become a cation and an electron. And the group 2s pretty much are the same way. Magnesium's kind of high on this list of who likes to get oxidized. But who would be down at the bottom? Who would like to get reduced? Well, that would probably be the nonmetals. And the top dog in the nonmetals is fluorine. It's the most electronegative. So sure enough, fluorine, F2, would love to gain 2 electrons to become 2 fluorides. It has a huge reduction potential. Even among the metals, you find that there are some metals that rust better than others. For instance, magnesium turns into magnesium oxide, the white powder that you find on those little silvery strips of magnesium. Iron's kind of up here because it likes to rust. Copper, not so much. Copper pennies, you leave them out. If you leave them out in the weather, sure enough, they'll tarnish a little bit. Copper oxide's sort of black, and so pennies will get darker. Silver tarnishes a little bit. They sell tarnish remover for silverware. Gold, not so much. Now you're getting down into the metals that are really kind of unreactive. Well, I got one quick little story I got to tell you. Let me just fade here. I got to go get something. I'll tell you about something about copper and silver here. Hold on just a second. Okay, for those of you who had me for Chem 130, you probably heard the story, so I apologize. But when I was growing up, on Saturday mornings, they had the show Mr. Wizard. It was this guy, Frank Herbert. He was an English teacher. But he got on the TV and he did these science experiments. And he'd do them live. And so sometimes they worked, sometimes they didn't. He had kids on, and it was more fun when the experiments didn't work. Because then they would spend the whole hour trying to figure out why it didn't work. Well, one day they were making a pinhole camera out of a coffee can. And I thought this was so cool. Metal coffee can, punched a hole in the bottom with a nail, and put a little flap over it made out of cardboard and a piece of tape. And then they had some photographic film, and they told you where you could go and get this stuff, and the chemicals, everything. So anyway, you developed the picture right inside the coffee can. I thought, well, this was cool. They propped it up between books. So I went down to Peoria Camera Shop, And these guys are like drug dealers. I mean, they loved back then when people had dark rooms and, you know, it was a hobby. They'd love to get people hooked on their chemicals. And so they gave me a whole bunch just to get me started. And some Dectol developer and stop bath and everything, and explained to me how to do everything, and explained to me what I had seen on Mr. Wizard show. So I went home, got a coffee can, punched a hole in it, and propped up some books just like they did, strapped my sister to a chair so that she wouldn't move while I took a picture of her, lifted a little flap on the coffee can, and exposed the film that I had put inside the lid, and developed it, and came out. I got a picture of my sister. I made a little print out of it with a piece of glass. I used all my mom's dishes from the kitchen to put the chemicals in, ruined a whole bunch of them. And I did this all on my attic stairway because it was the only place where there was a door on both ends where you could get it completely dark in the house. So anyway, I got hooked. And so, yeah, the drug dealers got me. So I was back down at Peoria Camera Shop all the time. And spent all my every dime I could get on chemicals and on new trays, and so I stopped ruining my mom's dishes. But anyway, then I got my father involved. He saw it, and he had heard somewhere that in the trays, that after you develop a lot of pictures, there's a lot of silver ions in there, because they use silver iodide as photosensitive, and that's the emulsion that's on the photographic paper. And so this would become rich in silver ions. Well, it turns out that copper is higher on this oxidation table than silver is. And so we would throw pennies in the bottom of the trays. Well, the copper and the pennies like to be the cation more so than the silver did, and they would change places. The copper would go into solution and become copper +2. The silver would sit down as silver 0, as a sludge of silver metal in the bottom of the tray. So we'd throw a handful of pennies in and exchange it for silver. Well, we'd filter out the silver from the trays, take it back down to Peoria Camera, and they would actually buy it from us. And so it was a nice exchange rate, and you could, you know, at least defray the cost of your chemicals. And my father just thought it was just such a cool electrochemical. I don't think he understood the electrochemistry involved there, but he just thought it was a cool exchange for the pennies to get the silver out of there. Now I got to show you a picture. This is of my cousin. This is one that we developed in our dark room. Once Dad got involved and I had money, then we got, you know, better equipment. But it was a lot of fun. So anyway, Mr. Wizard, highly recommend this dude. And as I was going through a library, one of the grade school libraries here in town, they were throwing out a lot of books. They had 2 Mr. Wizard books, so I have my favorites here. 400 Experiments in Science, and Mr. Wizard's Supermarket Science, must reads. All right, well, let's get back to electrochemistry. Okay, well, first we're going to look at galvanic, or what are called voltaic cells. These are cells that essentially have a spontaneous oxidation reduction reaction that happens, like a battery, where the minute you connect it, a spontaneous flow of electrons begins. At the end of the chapter, we're going to look at what are called electrolytic cells. These are cells that you have to push them with an applied voltage, for instance, like an electroplating. But first, let's look at batteries, the spontaneous flow of electrons. Okay, well, a very common oxidation reaction that we look at in this chapter is the reaction of zinc solid with copper ions. It turns out in that pecking order, zinc's kind of higher on the list than the copper, and it prefers to be an ion, more so than the copper. So if we put them in a position where we've got zinc in its solid state and copper in its ionic state, they would prefer to change places. The zinc would give up its electrons to the copper. It's the oxidation here with a loss of 2 electrons. The copper would be reduced, and it would gain the 2 electrons. Now, if we let them just deal directly with each other, for instance, if we took a piece of zinc metal and just sat it down in a solution that contained copper ions, and we would put it in there, say, as copper nitrate or copper sulfate, some soluble copper compound, so that we could get the copper ions on the dance floor. As soon as those copper ions ran into that zinc metal, this reaction happens spontaneously. It's got a negative delta G. It produces an actual voltage, which we're going to discuss here in a second. And so the copper essentially then gets reduced and picks up the electrons from the zinc. Well, the zinc then becomes water soluble and becomes zinc ions. The copper goes from being copper +2 to to metallic copper and begins to settle to the bottom of the beaker. So after a few minutes, we actually see a little pile of copper metal begin to accumulate at the bottom of the beaker. And you'll notice that the zinc metal begins to get eaten away. I'm exaggerating this, but it gets eaten up as the copper ions pick up the electrons and fall to the bottom. All right, well, in this case, there's an oxidation reduction reaction for certain going on there. The copper's picking up the electrons, the zinc's giving them up, and they're exchanging places. As a matter of fact, the blue color of that copper ion begins to diminish, and you see it get lighter and lighter and lighter in color because zinc is colorless, but those copper plus 2 ions are usually a nice blue in solution. Well, here's the problem. We're letting these two half reactions, remember there's an oxidation half reaction going on here, and a reduction half reaction. What we need to do is get them separated from each other. Get these two reactions to happen in separate beakers, and we'll allow the electrons to get transferred, but on our terms. We'll make them travel through an external circuit in order to get from the zinc to the copper. That way we can kind of harness them to do a little bit of work. All right, well, let me make a little room here. Okay, so here's a nice simple battery then, constructed from the oxidation reduction reaction we just had on the board. Now, what I've done is I took a beaker and made a solution of zinc plus 2 ions. For instance, about a 1 molar solution of zinc nitrate. And so that would be zinc plus 2. So we've got a 1 molar solution of zinc plus 2 ions out here. I'm going to put a zinc electrode into that beaker so that this reaction could run in either direction. The zinc could become zinc plus 2, or the zinc plus 2 could plate out onto the electrode as a zinc metal atom. All right, so it has the potential to go either direction. In the other beaker, I put 1 molar copper nitrate, copper plus 2 ions, and in its beaker, I put a strip of copper metal. So likewise, we could establish an equilibrium here where it could run in either direction. The copper plus 2 could plate out and become copper, or the copper could oxidize and become copper plus 2. Well, again, we said that the zinc really does have a bigger oxidation potential than the copper. And so it loves to become the ion, more so than the copper does. So it's very likely that this is what's going to happen. As we connect these two together, we find that electrons are being produced by the zinc as it wants to become a zinc plus 2 ion. The electrons want to get over to that other beaker because copper plus 2 would much prefer to be copper metal. The electrons actually travel through the external circuit then, 2 of them. And now there's electrons coating this electrode. Well, that's attractive to those copper plus 2 ions. So sure enough, as this electrode begins to get eaten up, as the zinc begins to erode into the solution and form zinc plus 2 ions, the electrons from that oxidation travel through the external circuit and end up on that copper electrode, where this electrode begins to get a little fatter with copper as it begins to plate out. All right, well, it turns out that, yeah, there is a little bit of force with which this is a spontaneous reaction, so there's got to be some kind of force pushing the electrons or pulling the electrons through that external circuit. Well, it turns out that zinc, its oxidation potential, is actually pushing to the tune of 0.76 volts, meaning it loves to get rid of electrons. And by the way, I should point this out as we get into this voltage discussion. When a reaction has a spontaneous voltage, it's going to be a positive number, a positive voltage. Now, that is unlike most state functions or things that we've looked at in the past, like delta H's are usually negative when they're more favorable, and delta G's would be negative. But in this case, we want positive voltages for spontaneity. All right, and you'll see that that's consistent with the mathematics that we're using, but that's the sign convention. So it turns out, yeah, zinc loves to be oxidized to zinc plus 2, and it does it to the tune of 0.76 volts. Now remember, that's the pressure with which it's pushing the electrons away from it. All right, how many joules per coulomb of charge it's willing to push them with. Well, it turns out that copper has a reduction potential. It pulls on the electrons to the tune of positive 0.34 volts. So copper's got a little bit of a reduction potential to pull the electrons in. So this is its pull, and this is the zinc's push. Well, if we were to put a voltmeter here in the middle of this, the voltage that would be read between these two half cells, which is what they call them, half reaction in one half cell, half reaction in the other, the voltage here would be the sum of those two, 1.10 volts. That would be the theoretical voltage for a zinc-copper combination, given that we know the potentials for the zinc to give away the electrons and the potential for the copper to pull on the electrons. Now these voltages are listed in table 20.1. Hold on just a second, let me take a quick peek. Yes, in 20.1, all of the voltages for all of the half reactions that we're going to look at. And so you can see this is more just an arithmetic game. We're going to couple together an oxidation half reaction with a reduction half reaction. And I'm sorry, I said that exactly backward. Oxidation on this side, reduction on that side. And we're going to look at their potentials. How much force are they trying to push the electrons away from the oxidation half, and how hard are they pulling on the reduction half? That'll tell us the theoretical voltage for that cell. Now I have to explain something about batteries here first. The way that we've got this battery set up, it would only run for a few seconds and it would just stop. And it turns out it's a charge imbalance problem, because as copper plus 2 ions exit this solution, remember that they came to the dance with nitrates, so there's an equal number of cations and anions in this solution. Nature likes that, same number of positives as negatives. But as the copper plus 2s disappear from the solution, suddenly this solution becomes too negative. There's too many anions and not enough cations to make up for it. Well, the opposite happens in this half cell, because here the cations are building up. Well, once the cation buildup begins and the anion buildup begins here, the battery stops. Because anions in this solution are going to repel electrons, cations in here are not going to let the electrons go, so consequently the battery just quits. Well, it turns out that there's a mechanical way that we can fix that imbalance, and it's something called a salt bridge. Now what they do is, and this is what we used to do back at University of Illinois, we used to do an electrochemistry lab where we actually had students set up beakers of solutions, put metal strips in them, we'd put voltmeters on there and measure the voltage. We went through gallons and gallons and gallons of these nitrate solutions because they were big 250 ml beakers. But we also had to make these salt bridges. Now what a salt bridge was, we took a U-shaped glass tube, and in that U-shaped tube, the night before we did the lab, we would make some jello, clear gelatin, but we wouldn't make it with just water, we'd make it with potassium chloride. So it was salty jello. And we'd put them in these U-shaped tubes and then stuff glass wool into the openings. We'd have them upright, obviously, and we'd let them sit in the refrigerator overnight and set up so they were just gelatinous inside this U-shaped tube, stuffed with a little bit of fiberglass wool on each end, just to keep it from leaking out. Well, then we would flip them over and put them into these two beakers. Well, there's potassium ions and chloride ions in a gel then that are free to migrate. Well, over here where cations begin to build up in this solution, chloride ions would begin to migrate out of our salt bridge to make up for the excess positive charge in this half cell. And the potassiums would begin to move out into this solution to make up for the missing copper cations. So it would replenish the cations here, it would add additional anions here, and suddenly the charge imbalance and the battery would just continue to run and continue to run. Now naturally it'll run until the zinc electrode's completely eaten up or the copper ions are completely exhausted from this solution. But as long as we keep the salt bridge in there and keep the ion balance just right, it'll continue to go until the last dog dies. Well, you'll find later in this chapter, I'm going to show you some cross-sectional photos of batteries, like regular Leclanche dry cell batteries. Sure enough, in between the two portions of the battery where the oxidation half reaction happens and the reduction half reaction happens, there's usually a porous paper filter that's put between the two, and it's soaked in an electrolyte. Alkaline batteries soak them in potassium hydroxide, hence the word alkaline battery. And sure enough, that salt bridge between the two half reactions helps to maintain the charge imbalance at the two ends of the battery and allows the battery to continue to run. All right, well, let's look a little bit deeper here then at how would the voltage of these batteries then be affected, say, by the concentration of the ions that are there. It seems pretty clear that if we really charged it up with copper ions on this side, that it might run a little bit better. And that sure enough is the case. But before we do, let's just do a little bit of nuts and bolts just to make this a little easier. I want to show you some shorthand notations for how we figure out the voltages of cells. I forgot a couple things here. The force with which these electrons are being pushed through there is called the electromotive force, EMF. They use that term throughout the chapter. It's measured in volts, and so I just wanted to get that term out here before we got too much further. Also, I mentioned the word electrode when I mentioned these metal strips that we would put into the solutions. Well, it turns out that the electrode where the reduction is happening is referred to as the cathode. The electrode where the oxidation is happening is referred to as the anode. And I'd like you to be familiar with those two terms because they come up obviously since we're going to look at oxidations and reductions. And an easy way to remember is that oxidation starts with a vowel, so does anode. Reduction and cathode both start with consonants. Easy enough to remember. Okay, well, I think we got all the terminology in there that we want. Let's look a little closer at table 20.1. Okay, before we get to table 20.1, I mentioned this shorthand notation for writing out a cell, an entire galvanic cell or electrolytic cell. You could do it either way, whether it's spontaneous or not. Generally, what they do is they write the oxidation half reaction on the left and the reduction half reaction on the right. They just simply put a bar here to represent a phase boundary, meaning the boundary between the aqueous zinc ions and the solid zinc electrode, that there's a phase boundary where the two of those are in contact with one another, where an equilibrium could be established. This double bar stands for the salt bridge. So in essence here, they're just showing the reactant and the product in the oxidation half reaction. So they know that it's going from zinc to zinc plus 2. Generally, they'll tell you the molarity of that zinc ion there because, again, later we'll see that that affects the voltage and consequently we'll need that number. Now, on the reduction half reaction, notice that, again, they show the reactant and then the product because in this case the reactant's the copper plus 2. It's being reduced to the copper solid. And again, they've shown the molarity of the copper plus 2 ion that's aqueous. Here, again, is a phase boundary between the two, the aqueous copper ion and the solid copper. All right, well, this is handy because, again, we don't want to have to draw pictures of beakers and salt bridges all the time. If we can just in one line show you, well, this is the oxidation half of the battery, this is the reduction half of the battery, let's figure out what kind of voltage we could get out of it. This seems to be a little bit easier way to do it. Okay, well, now let's look at table 20.1. Okay, well, here's kind of a truncated version of table 20.1 in your textbook. Be sure to dog-ear that page because you're going to be referring to this page to do a lot of the homework problems. You need these voltages. Now, essentially then, it's a list of reduction potentials. Potential, I mean the EMF, the electromotive force with which each of these elements pulls on electrons. Now notice that things that like to be reduced, like fluorine, would have a positive voltage, where things that don't like to be reduced, like lithium, have a very, very negative voltage down at the very bottom. All right, well, again, it's not likely that lithium is going to run as a reduction. It's probably going to run as an oxidation in your battery, and you're clever enough to know that that would change the sign of the voltage. So rather than have a table of oxidations and a table of reductions, where the reactions are simply flipped and the numbers have their signs changed, They just give you one table. Now you understand that when you make a battery, you can't have two reductions. You have to have an oxidation and a reduction. So again, you're clever enough to figure out, well, one of these I'm going to have to flip over and change the sign of its voltage before I add the two together. Because again, the potential that you get from a battery is the sum of the oxidation potential, how hard the oxidation and half reaction pushes, summed together with how much of a reduction potential the other half of the battery has, how hard it's pulling. Now one thing you'll notice here, in the middle of this table is hydrogen with 0 volts. Now this is because, and this is one of those recall moments, if you recall back when we talked about the standard heats of formation, I always start off with the analogy of measuring the height of a mountain, for instance. We know that Mount McKinley is 23,000 some odd feet tall. Well, and if you ask anybody, well, where was that measured from? They all know, well, it's measured from sea level. So apparently we all agreed that that's where we would measure the height of mountains. I mean, technically, really, if you want the height of a mountain, you'd have to measure from the center of the earth. That's the actual height. But no, we all agreed on a different reference point that made more sense. So we chose sea level as our arbitrary reference point from which we measure elevations. Well, it turns out with heats of formation, we did the same thing. We chose the elements to be sea level, 0 heats of formation. Anything that took kilojoules to manufacture went above sea level. Anything that gave up kilojoules was below sea level. Then we could take the differences between things. But we arbitrarily chose that reference point because we're really only looking at the relative differences between potentials. All right, well, they did the same thing with voltages. They thought, well, we know that there are things that really want the electrons and things that really don't. Who's in the middle of the stack? Let's pick the one in the middle and call it 0. And then we'll call that sea level, and we'll measure above that and below that. Well, sure enough, the one that was in the middle of the stack was hydrogen. They devised kind of a clever electrode for measuring other half cells compared to hydrogen. So all of these voltages are simply measured in comparison to the reduction of hydrogen. And again, that's just our arbitrary sea level. All right, well, here's how this works then. Suppose I want to make a battery, and let's use something like silver on one end and cadmium on the other. All right, well, let me get rid of everybody else. Yeah. Okay, so I want to make a battery out of silver and cadmium. Both of these are listed in the table as reductions, but I know my battery is not going to be composed of 2 reductions. There's got to be an oxidation and a reduction. And I want the voltage to come out positive when I add these two together. Well, it appears that this one likes to be reduced because it's got a nice positive voltage, but the cadmium does not like to be reduced. So it seems logical, let's reverse this one. Let's make the cadmium the oxidation. So in my shorthand notation, I would write it like this. Cadmium going to cadmium plus 2. And let's presume that everybody's 1 molar, standard voltages. I didn't mention that earlier, but those standard voltages in table 20.1 assume that everything is in standard conditions. That means 1 molar concentrations for everybody. Again, remember, later we're going to look at how if you change those molarities, voltages change subtly. All right, well, the cadmium would go to cadmium plus 2. Let's put a salt bridge here, and let's run the silver as a reduction. Ag plus, aqueous, 1 molar, going to Ag, 0, silver solid. So that would be the shorthand notation. I'm actually running this one as an oxidation in reverse. Well, as a matter of fact, let me rewrite it. Now it's cadmium going to cadmium plus 2 electrons. That E naught, that standard EMF, is not going to be minus, it's going to be positive 0.40 volts. All right, so now I've got my oxidation half reaction, I've got my reduction half reaction. Simple to figure out, well, what's going to be the voltage of this cell? Well, I'm getting 0.4 volts here, I'm getting 0.8 volts here. Looks like I get a grand total of 1.2 volts as my standard E naught of this cell. All right, so you can see that this does take a little bit of logic because we're going to show you 2 half reactions that are reductions and say, well, you know, let's make a battery out of these 2. Kind of up to you to figure out, well, which one of them am I going to have to flip? because I know one of them has to be an oxidation. Well, you'll flip the one that's obviously going to be more negative so that it will become positive. That way you can actually get a positive voltage for your battery. Easy enough to write out its shorthand notation. Now, let's take this up a notch. What if I said, well, can you write me out the overall balanced oxidation reduction reaction for that? Well, now remember, we got this 1.2 volts, so let's do this. Okay, well, we're running the cadmium as an oxidation, so that means the cadmium's going from cadmium 0 to cadmium plus 2. The silver, on the other hand, is going from silver plus 1 to silver 0. Right? It's a reduction. Now notice that even though it's balanced by head count, it's not balanced by electron exchange. Because the cadmium's losing 2 electrons. There's an oxidation right there with 2. This reduction only has 1. So that means I'd have to double the silvers for this to happen. Now the reason I bring this up is because the urge now to double the voltage for the silvers is almost overwhelming. But it turns out with this, we don't double it. Normally with like delta H's, if we doubled something, we always doubled it. But not with voltages. And here, let me explain quickly why. It turns out that the silvers are trying to pick up electrons to the tune of 0.8 volts. All right, so that means essentially then that they're putting that many joules per coulomb of charge when they're going up to whip it through the tube. They're actually pulling on the other end at 0.8 joules per coulomb of charge that I'm throwing through there. Well, it turns out it doesn't matter how many silvers you have lined up. Each one is going to come up to bat and only put 0.8 joules per coulomb on that charge as it's going through the tube. So again, in the equation, it doesn't matter if there's 2 of them, 3 of them, 5 of them. Every time one of them comes up to bat, 0.8 joules is all they can produce. All right, so again, fight the urge when you see that, oh, I had to bump that coefficient by a factor of 2. Don't go back and bump the voltages. It's based strictly on those numbers that you get out of table 20.1. You don't have to do anything to them. All right, well, let's do a couple more just to cement the deal here. Okay, here's an interesting one. And again, this is in the section 20.4 in your text where they're talking about predicting the spontaneity of a reaction. You know, which way would it run to be spontaneous? Well, again, positive voltage is what we want. Now, what if you pit 2 things that neither of them really look like they want to be reduced? Well, it turns out one of them wants to be reduced less than the other. And so consequently, if I were to look at a nickel-cadmium battery, where I've got a potential nickel reduction here, nickel plus 2, gives a voltage of 0.23 volts, negative 0.23, so it's not spontaneous. Cadmium, on the other hand, is even less spontaneous. Cadmium plus 2 electrons going to cadmium is minus 0.40 volts. Now, I'm going to have to reverse the sign of one of these two, and I want to do it in such a way that when they're added together, it ends up being positive. So it's pretty clear I need to change the cadmium. So if that's the case, then the shorthand notation for this, and again, I'm not going to run this as a reduction. I'm going to run it as an oxidation. Cadmium going to cadmium plus 2 electrons. The E naught now is going to be positive 0.40 volts. And sure enough, I'll get a positive, what, difference there is 0.17. I get a positive 0.17 volts out of this. Let me write out the shorthand notation for that. The shorthand notation would be, and again, the oxidation we always put on the left. So it'd be cadmium going to cadmium plus 2, and I'll put here 1 molar. Salt bridge, it's nickel plus 2, 1 molar, going to nickel as a solid. Okay, I got cadmium as a solid. All right, so there's the shorthand notation for it. Now, later in the chapter, they're going to want you to write out the overall oxidation reduction reaction and make sure that it's balanced. Now remember, balancing the oxidation reduction reaction does not change these voltages. Once we established that this was going to be our oxidation, this was our reduction, we simply use the numbers straight away from table 20.1. All right, but let me erase this and we'll write out the overall reaction. Now in this case, we've got cadmium as a reactant, as a solid. On the other side of the arrow, we know it's going to become cadmium plus 2. So there's our oxidation. Our reduction is the nickel. So it's nickel plus 2 on this side. Again, that's the reactant. This is the product. So these are both going in this direction. This being the oxidation, this being the reduction. So this would go to nickel solid. All right, well, it looks as if it's balanced electron-wise because the cadmium oxidation shows a loss of 2 electrons. And the nickel reduction is a loss of 2. Everybody see how that works? Okay, so again, writing out the shorthand notation is really not too tough for half cells. As a matter of fact, we'll do a couple more. Let me erase this. All right, one of the examples at the end of section 20.4 in your textbook asks this question. It says, could you predict if this reaction is spontaneous? And they give you 2 of them to try. Well, the first one was zinc, metal, and nickel plus 2 going to nickel, metal, and zinc plus 2. Again, remember that if you're looking at table 20.1, the reduction for nickel plus 2 is listed, sure enough, as minus, what was that, 0.23 volts that we had. In its reduction mode, picking up electrons, sure enough, that's the number from table 20.1. However, the oxidation of the zinc, well, if you look up its reduction potential on table 20.1, it's got a reduction potential of minus 0.76 volts, but we're not running it as a reduction. We're running it as an oxidation, positive 0.76 volts. I guess their question then was, well, if I add these 2 voltages together, is this going to be a positive voltage and end up being spontaneous? And the answer is yes. All right, well, what about the zinc plus the calcium? Well, it turns out again, zinc going to zinc plus 2 is a positive 0.76 volts. But the reduction of calcium turns out to be, let me find the number here. Reduction of calcium minus 2.76 volts. Apparently it doesn't like that. It prefers to be the cation, even more so than the zinc. So no, this reaction would not be spontaneous. As a matter of fact, the reverse reaction would be spontaneous. So this is why table 20.1 is kind of important to this whole idea. They're going to link together 2 half reactions for you and just simply ask you, let's come up with the voltage. Well, just keep in mind that the reduction has to have its sign changed when you're running it as an oxidation. Then simply add your 2 half reactions together, add the 2 voltages together. Well, I mentioned before that hydrogen electrode that they use to standardize all the other voltages in table 20.1, that they kind of chose that as the sea level voltage from which they would measure all other potentials, and they assigned it a value of 0. That was really kind of arbitrary, but as long as we all agree that that's what we're measuring from, then the relative difference of potentials will still be the same. All right, well, the way they set this up was kind of interesting. A standard hydrogen electrode looks like this. It has the potential to have hydrogen gas, or 2 hydrogen ions, pick up 2 electrons to become H2. All right, well, that's the half reaction that could potentially happen here, but it could also run in reverse. So they put hydrogen gas in a glass sleeve, 1 atmosphere of pressure, so that it's basically got liquid right up to the liquid that's in the beaker here with this tube inverted. They put a sealed platinum electrode in there that dips down into the liquid that contains hydrogen ions. So right here at this interface, you could have hydrogen ions picking up electrons to become hydrogen gas, or vice versa, you could have hydrogen gas giving up 2 electrons and becoming hydrogen ions and forcing those electrons through the circuit. All right, so if we wanted to measure the voltage of another half cell compared to the hydrogen one, all we'd have to do is take a solution of that metal ion, whether it's zinc or cadmium, whatever it is, make a 1 molar solution of it, put a strip of metal in there made out of exactly the same stuff, and connect this to our hydrogen half cell. All right, well, here's what's interesting. If the electrons flow this way, then we get a positive voltage, and that means that this one likes to be reduced more so than the hydrogen. So it would go above hydrogen on the table in reduction potential, and it would be given a positive value. If, however, we hook up that half cell to the hydrogen and the electrons flow the other way, and it gives us a negative value for voltage, well, that means then that this thing really would prefer to be oxidized and ends up being below the hydrogen on the reduction table. All right, so again, they had to pick somebody to be in the middle, and it was hydrogen that ended up having that 0 voltage. Everything else just measured relative to it. All right, well, now let's look at a relationship between the work that a battery can do and the actual voltage. Remember, I said that the real power has to do not only with how hard the electrons are being pushed through there, but how many electrons actually get pushed through the tube. So let's look a little bit at the work potential of a battery. Okay, well, in our thermodynamics chapter, we talked about work, and really work, if you boil it all down, turns out to be the work max that you can get out of a system is essentially delta G, the difference between the entropy hill and the heat hill. But in terms of a battery, if I were looking at, again, the analogy of water going through a hose, if I want to know how much work I could get out of that water as it's coming out the other end of the hose, I'd need to know how many gallons per minute are going through there and with what pressure they're going through. All right, so in that case, the work would have to do with the number of moles of electrons that are actually being pushed through the wire. That's like how many gallons of water are going through. Well, they use the symbol N to stand for the moles of electrons transferred. All right, and we know that the voltage would tell us then, well, how hard are you pushing those moles of electrons through there? So we need the standard voltage. So this would be joules per coulomb of charge. And just to keep the sign convention correct, we need a negative sign here because if the battery's doing work on its surroundings, it's going to be a negative value of joules. But there's one thing missing in the middle here, is I know how many joules per coulomb and I know how many moles of electrons. What I need to know is, well, how many coulombs are there on a mole of electrons? That conversion factor is missing. Well, I alluded to it earlier. It's called Faraday's constant. If we took the charge on a single electron and multiplied it by Avogadro's number, it turned out to be Faraday's constant, 96,500 coulombs per mole of electrons. As a matter of fact, let's put that down here. 96,500 coulombs per mole of electrons. All right, so then you can see that this is not a really hard calculation. If I know the voltage a battery can produce, and I looked at how many moles of electrons actually pass through over a given period amount of time, not too hard to figure out how much work the battery did. As a matter of fact, let's do a quick example. I'll get rid of this and we'll come back. Okay, well, let's look at the battery we looked at earlier, cadmium-silver battery. Now here's the overall reaction. Cadmium being oxidized to cadmium plus 2, loss of 2 electrons, 2 silver plus 1s going to 2 silver metals, a gain of 2 electrons. Now it turns out that the cadmium, or the silver reduction potential, when we look it up in table 20.1, is positive 0.80 volts. Doesn't matter if it's for 1 silver, 2, 4, 10, doesn't matter. That value came straight from table 20.1. And the cadmium, when we look up its reduction potential, was minus 0.4, but we're running it as an oxidation. So that means it's positive 0.4. That gave us a total of positive 1.2 volts for this reaction. Now, if I were to ask you, well, how much work could that battery do if we were to run an entire mole of cadmium through here? Now, a mole of cadmium is quite a bit. I forget the molecular weight, but that's a sizable amount, so it'd have to be a pretty big battery. But let's do it for just 1 mole. Well, again, the work for 1 mole of cadmium, which is what I've got listed here, would be a negative. Now, the moles of electrons transferred was the first thing we had in here was N, F, and the voltage. Well, there's the voltage, but what would the value of N be? Well, it looks as if the way the reaction is written right now, for 1 mole of cadmium, there would be 2 moles of electrons transferred through the wire, right? If we could physically segregate the cadmium half reaction from the silver, then for 1 mole of it to get oxidized, 2 moles of electrons would have to pass through the system. So this would be a 2. Faraday's constant, and so let's put the units in here so you can see how this all works out. This is 2 moles of electrons, 96,500 coulombs per mole of electrons, and 1.20 joules per coulomb. That's what a volt is, and that's the voltage of our cell. All right, well, in that case, if we multiply this all out, it comes out to be, what I have here, 2.32 times 10 to the 5th joules, or that'd be 232 kilojoules. All right, so pretty simple calculation. If you've got table 20.1 sitting right there in front of you, and you've got the reaction all written out, it's not hard to come up with its voltage. What you have to deduce from the overall reaction, though, is what was the value of N, the number of moles of electrons that was exchanged. Notice that you'd have to have the equation balanced in order to get that. You wouldn't get that from the shorthand notation. Remember, the shorthand notation doesn't show any coefficients. And so, again, you'd have to balance it out to get that value of N. Okay, well, you knew this couldn't slip by. It turns out that, yeah, the equilibrium constant somehow gets worked into this chapter. Equilibrium seems to pervade everything in Chem 132. Well, we just established this idea that you could calculate the work that was done by a battery by knowing how many moles of electrons are transferred and the voltage and Faraday's constant. But back in the last chapter, we also had a relationship between delta G naught and the equilibrium constant. Well, since these two are equal to each other, the work max that you can get out of a system is equal to delta G naught. We could say, well, this is minus NF E naught. This, we established in the last chapter, was minus RT ln of K. Well, right there, you can see there's a mathematical relationship then between the voltage of a cell and its equilibrium constant. Well, we can't pass that up. We're going to have to derive an equation that relates the two. But it's awful ugly the way it is now, so let's pretty it up a little bit. I'm going to go ahead and get rid of the negative signs on both sides. And I'm going to divide both sides by NF. So I've got E naught is equal to RT over NF ln of K. So it already looks a lot prettier right there, where you can see a relationship then between E naught and K. And the K is large, the voltage is going to be large, which kind of makes sense that if you've got a big potential for a cell to run forward, very likely its equilibrium is going to favor the product side of the reaction. So that makes logical sense. Now, before I finish this equation, we can actually pretty it up quite a bit more. There's a lot of constants out here that we can lump together. But before I do, it turns out that the book doesn't like to use the natural log here. They like to use log base 10. Well, there's a relationship that the ln of x is actually equal to the log of x, but there's a fudge factor that goes in here. It's 2.303. You see that number a lot pop up in equations where they've switched from natural log to log base 10. I'm going to do that right here. I'm just going to go ahead and make this log k, and I'm going to put the 2.303 out in front. RT log of k. All right, so now we're kind of set for at least condensing all of these constants. Now notice something here. The only thing that's a variable in all of this is n. That could change from situation to situation depending on the balanced redox equation. Remember, that's the number of electrons exchanged in the balanced equation. But F is Faraday's constant. The temperature, since we're doing this at standard conditions, is 25 centigrade or 298 Kelvin. R is a constant, and we'd have to use the 8.314 R because that would be in joules. And remember that voltage is in joules per coulomb. All right, well, it turns out that if we were to lump together all of these constants that are out here into one number, just crunch them all down into one number, it turns out to equal 0.0591. The only thing left as a variable is n. And if you check, the units do come out joules per K, or joules per coulomb, and n cancels out with the Faraday's constant being coulombs per mole of electrons. So everything works out for this to be in joules per coulomb, the voltage. All right, well, now that's kind of a handy relationship. If I want to know the relationship between the voltage and the equilibrium constant, the only other thing I need to know is what's the value of N, the number of electrons exchanged in that particular oxidation reduction reaction. All right, well, let's do a problem like that. Okay, well, here's an example of what we were just talking about. If we were to look back at an example we had earlier, cadmium and nickel getting together, to nickel plus 2 being reduced, picking up 2 electrons, cadmium going to cadmium plus 2, losing 2 electrons, that means that the N value here is 2. That's the number of electrons exchanged. Remember, these numbers can get big. There were some where we had to take this up to a common multiple of 10. So there are reactions where the N value can get quite large, so don't let that throw you. The voltage, if you recall, when we looked up the reduction potential of the nickel, I think was a positive 0.23 or a negative 0.23, but this was a positive 0.40, so it gave us an overall voltage of 0.17 volts. All right, so if I said, well, could we find that equilibrium constant? This battery will run forward probably for quite a while before it reaches equilibrium, so its equilibrium constant would probably be kind of large. Well, we just established the relationship that E naught is equal to 0.0591 over N log of K. All right, well, we've got everything. We know the voltage, we know the N value, we just don't know K. All right, so in this case, this is going to be 0.17 volts is 0.0591 over 2 log of K. Let's go ahead and rearrange then. The log of K is going to be the 0.17 times 2 divided by 0.0591. So the log of K would equal, let me get my calculator. Can you see all that on the screen? I guess so. 0.17 times 2 divided by 0.0591. The log of K came out to be 5.7530. 5.7530. Now the reason I carried some illegal sig figs there is because I'm about to take an inverse log. Remember, this is 10 to that power. So K is going to be 10 to the 5.7530. Let me do that. I got 5.66, 10 to the positive fifth. So there's my equilibrium constant for this battery. It looks as if it's going to run pretty much to completion before it reaches equilibrium. That's a pretty large equilibrium constant. All right, so we've looked at these relationships before between delta G and K. Well, now we're looking at the relationship between the voltage of a cell and K. And it makes logical sense that as the K value goes up, so goes the voltage, because they both indicate spontaneity. Okay, so in this module then, we've covered oxidation reduction reactions and how to balance them. Then we began to look at this pecking order of, well, who likes to be oxidized, who likes to be reduced, and if we tie those together, is there a certain potential for the electrons to move from one to the other? We showed how the voltages were measured, and table 20.1, which shows the potential voltages for all of those different half reactions, and how we can calculate then the voltage for a simple battery, given the two half reactions. Then we began to look, well, how much work can we get out of the battery? So that brought up a little bit of our thermodynamics chapter. And then finally here, we just simply looked at the relationship between the voltage of the battery and the equilibrium constant. All right, well, in our next section, we're going to look at something called the Nernst equation. And this has to do with how the molarities of the ions affect the voltages. And this is what our next lab is going to be on, is on the Nernst equation. And so we may kick that down the road a little ways so that we can get this lecture under our belt before we do the lab. But I think you'll see that there's a way that you can actually squeeze a little extra voltage out of a battery if you're willing to kind of tilt the playing field in your favor. So anyway, this is covered in our next topic on the Nernst equation. If you've got any questions, again, just give me a shout, and we'll keep our regular meetings on Monday and Wednesday at 5:30 and bring any homework questions that you might have. So anyway, I'll see you next lecture. We'll cover the last half of chapter 20.